not to be confused with sp mixing in molecular orbital theory. See molecular orbital diagram. In chemistry, hybridization is the concept of mixing atomic orbitals into new hybrid orbitals suitable for the pairing of electrons to form chemical bonds in valence bond theory. Hybrid orbitals are very useful in the explanation of molecular geometry and atomic bonding properties. Although sometimes taught together with the valence shell electron-pair repulsion theory, valence bond and hybridization are in fact not related to the VSEPR model. Historical development: chemist Linus Pauling first developed the hybridization theory in 1931 in order to explain the structure of simple molecules such as methane using atomic orbitals. Pauling pointed out that a carbon atom forms 4 bonds by using 1s and 3p orbitals, so that it might be inferred that a carbon atom would form 3 bonds at right angles and a 4th weaker bond using the s orbital in some arbitrary direction. In reality, however, methane has 4 bonds of equivalent strength separated by the tetrahedral bond angle of 109.5 degree. Pauling explained this by supposing that in the presence of 4 hydrogen atoms, the s and p orbitals form 4 equivalent combinations or hybrid orbitals, each denoted by sp3 to indicate its composition, which are directed along the 4 CH bonds. This concept was developed for such simple chemical systems, but the approach was later applied more widely, and today it is considered an effective heuristic for rationalizing the structures of organic compounds. Orbitals are a model representation of the behavior of electrons within molecules. In the case of simple hybridization, this approximation is based on atomic orbitals, similar to those obtained for the hydrogen atom, the only neutral atom for which the Schrödinger equation can be solved exactly. In heavier atoms, such as carbon, nitrogen, and oxygen, the atomic orbitals used are the 2s and 2p orbitals, similar to excited state orbitals for hydrogen. Hybrid orbitals are assumed to be mixtures of these atomic orbitals, superimposed on each other in various proportions. It provides a quantum mechanical insight to Lewis structures. Hybridization theory finds its use mainly in organic chemistry. SPX and SDX terminology: this terminology describes the weight of the respective components of a hybrid orbital. For example, in methane, the C-hybrid orbital which forms each carbon-hydrogen bond consists of 25% S character and 75% P character and is thus described as sp3 hybridized. Quantum mechanics describes this hybrid as an sp3 wave function of the form n, s plus h3 pi fluorine, where n is a normalization constant and pi fluorine is a p orbital directed along the CH axis to form a sigma bond. The ratio of coefficients is H3 in this example. Since the electron density associated with an orbital is proportional to the square of the wave function, the ratio of p character to s character is I2 equals 3. The p character or the weight of the p component is N2I2 equals 3/4. For atoms forming equivalent hybrids with no lone pairs, there is a correspondence to the number and type of orbitals used. Thus sp3 hybrids in methane are formed from 1s and 3p orbitals. However, in other cases, there may be no such correspondence. For example, the 2 bond-forming hybrid orbitals of oxygen and water can be described as sp4, which means that they have 20% s character and 80% p character, but does not imply that they are formed from 1s and 4p orbitals. As a result, the amount of p character is not restricted to integer values. That is, hybridizations like Sp2.5 are also readily described. For more information, see variable hybridization. An analogous notation is used to describe SDX hybrids. For example, the permanganate ion has Sd3 hybridization with orbitals that are 25% s and 75% d. Types of hybridization: sp3 hybrids. Hybridization describes the bonding atoms from an atom's point of view. That is, for a tetrahedrally coordinated carbon, the carbon should have 4 orbitals with the correct symmetry to bond to the 4 hydrogen atoms. Carbon's ground state configuration is 1s2 2s2 2px1 2py1 or more easily read The carbon atom can utilize its two singly occupied p-type orbitals to form two covalent bonds with two hydrogen atoms, yielding the free radical methylene CH2, the simplest of the carbons. The carbon atom can also bond to four hydrogen atoms by an excitation of an electron from the doubly occupied 2s orbital to the empty 2p orbital, so that there are four singly occupied orbitals. As the energy released by formation of two additional bonds more than compensates for the excitation energy required, the formation of four CH bonds is energetically favored. Quantum mechanically, the lowest energy is obtained if the four bonds are equivalent, which requires that they be formed from equivalent orbitals on the carbon. A set of four equivalent orbitals can be obtained which are linear combinations of the valence shell S and p wave functions, which are the four sp3 hybrids. In CH4, four sp3 hybrid orbitals are overlapped by hydrogen 1s orbitals, yielding four ifluorine bonds of equal length and strength. Translates into sp2 hybrids. Other carbon-based compounds and other molecules may be explained in a similar way as methane. For example, ethane has a double bond between the carbons. For this molecule, carbon will sp2 hybridize, because one I- bond is required for the double bond between the carbons, and only three ifluorine bonds are formed per carbon atom. In sp2 hybridization, the 2s orbital is mixed with only two of the three available 2p orbitals, forming a total of three sp2 orbitals with one p orbital remaining. In ethylene, the two carbon atoms form a ifluorine bond by overlapping two sp2 orbitals, and each carbon atom forms two covalent bonds with hydrogen by sp2 overlap, all with 120° angles. The I- bond between the carbon atoms perpendicular to the molecular plane is formed by two pi-2p overlap. The hydrogen-carbon bonds are all of equal strength and length, which agrees with experimental data, sp hybrids. The chemical bonding in compounds such as alkanes with triple bonds is explained by sp hybridization. In this model, the 2s orbital mixes with only one of the three p orbitals, resulting in two sp orbitals and two remaining unchanged p orbitals. The chemical bonding in acetylene consists of sp overlap between the two carbon atoms, forming a ifluorine bond, and two additional I- bonds formed by pi-p overlap. Each carbon also bonds to hydrogen in a ifluorine's I-sp overlap at 180° angles. Hybridization and molecule shape. Hybridization helps to explain molecule shapes since the angles between bonds are equal to the angles between hybrid orbitals, as explained above for the tetrahedral geometry of methane. As another example, the three sp2 hybrid orbitals are at angles of 120° to each other, so this hybridization favors trigonal planar molecular geometry with bond angles of 120°. Other examples are given in the table below. Main group compounds with lone pairs. For main group compounds with lone electron pairs, the s orbital lone pair can be hybridized to a certain extent with the bond pairs. This is analogous to sp mixing in molecular orbital theory, and maximizes energetic stability according to the Walsh diagram for the molecule. Trigonal pyramidal, the s orbital can be hybridized with the 3p orbital bonds to give bond angles greater than 90°. X. NH3. Bent. The s orbital lone pair can be hybridized with the 2p orbital bonds to give bond angles greater than 90°. The out-of-plane p orbital can either be a lone pair or pi bond. If it is a lone pair, the in-plane and out-of-plane lone pairs are inequivalent, contrary to the common picture depicted by VSEPR theory. X. SO2, H2O. Monocoordinate, the s orbital lone pair can be hybridized with a p orbital bond. The two out-of-line p orbitals can either be lone pairs or pi bonds. The p orbital lone pairs are not equivalent to the s-rich lone pair. X company, SO, HF. Hybridization of hypervalent molecules. Traditional description. In general chemistry courses and mainstream textbooks, hybridization is often presented for main group AX5 and above, as well as for transition metal complexes, using the hybridization scheme first proposed by Pauling. In this notation, d orbitals of main group atoms are listed after the s and p orbitals since they have the same principal quantum number, while d orbitals of transition metals are listed first since the s and p orbitals have a higher n. Thus for AX5 molecules, sp3d hybridization in the p atom involves 3s, 3p and 3d orbitals, while dsp3 for Fe involves 3d, 4s and 4p orbitals. However, hybridization of s, p and d orbitals together is no longer accepted, as more recent calculations based on molecular orbital theory have shown that in main group molecules the d component is insignificant, while in transition metal complexes the p component is insignificant. Resonance description: as shown by computational chemistry, hypervalent molecules can only be stable given strongly polar bonds with electronegative ligands such as fluorine or oxygen to reduce the valence electron occupancy of the central atom to a maximum of 8. This requires an explanation that invokes sigma resonance in addition to hybridization, which implies that each resonance structure has its own hybridization scheme. As a guideline, all resonance structures have to obey the octet rule for main group compounds and the dodectet rule for transition metal complexes. Main group compounds with lone pairs: for hypervalent main group compounds with lone electron pairs, the bonding scheme can be split into two components, the resonant bonding component and the regular bonding component. The regular bonding component has the same description, while the resonant bonding component consists of resonating bonds utilizing p orbitals. The table below shows how each shape is related to the two components and their respective descriptions. Clarifying misconceptions: VSEPR electron domains and hybrid orbitals are different. The simplistic picture of hybridization taught in conjunction with VSEPR theory does not agree with high-level theoretical calculations despite its widespread usage in many textbooks. For example, following the guidelines of VSEPR, the hybridization of the oxygen and water is described with two equivalent lone electron pairs. However, molecular orbital calculations give orbitals that reflect the C2V symmetry of the molecule. One of the two lone pairs is in a pure p-type orbital, with its electron density perpendicular to the HA-H framework. The other lone pair is in an approximately sp0.8 orbital that is in the same plane as the HA-H bonding. Photoelectron spectra confirm the presence of two different energies for the non-bonded electrons. Exclusion of d orbitals in main group compounds. In 1990, Magnusson published a seminal work definitively excluding the role of d orbital hybridization in bonding in hypervalent compounds of second-row elements. This had long been a point of contention and confusion in describing these molecules using molecular orbital theory. Part of the confusion here originates from the fact that one must include d functions in the basis sets used to describe these compounds, and the contribution of the d function to the molecular wave function is large. These facts were historically interpreted to mean that d orbitals must be involved in bonding. However, Magnusson concludes in his work that d orbital involvement is not implicated in hypervalency. Exclusion of p orbitals in transition metal complexes. Similarly, p orbitals have long been thought to be utilized by transition metal centers in bonding with ligands, hence the 18-electron description. However, recent molecular orbital calculations have found that such p orbital participation in bonding is insignificant, even though the contribution of the p function to the molecular wave function is calculated to be somewhat larger than that of the d function in main group compounds. Hybridization theory versus molecular orbital theory. Hybridization theory is an integral part of organic chemistry and in general discussed together with molecular orbital theory in advanced organic chemistry textbooks, although for different reasons. One textbook notes that for drawing reaction mechanisms sometimes a classical bonding picture is needed with two atoms sharing two electrons. It also comments that predicting bond angles in methane with MO theory is not straightforward. Another textbook treats hybridization theory when explaining bonding in alkenes, and a third uses MO theory to explain bonding in hydrogen but hybridization theory for methane. Bonding orbitals formed from hybrid atomic orbitals may be considered as localized molecular orbitals, which can be formed from the delocalized orbitals of molecular orbital theory by an appropriate mathematical transformation. For molecules with a closed electron shell in the ground state, this transformation of the orbitals leaves the total many-electron wave function unchanged. The hybrid orbital description of the ground state is therefore equivalent to the delocalized orbital description for explaining the ground state total energy and electron density, as well as the molecular geometry which corresponds to the minimum value of the total energy. There is no such equivalence, however, for ionized or excited states with open electron shells. Hybrid orbitals cannot therefore be used to interpret photoelectron spectra, which measure the energies of ionized states, identified with delocalized orbital energies using Koopman's theorem. Nor can they be used to interpret UV visible spectra which correspond to electronic transitions between delocalized orbitals. From a pedagogical perspective, the hybridization approach tends to overemphasize localization of bonding electrons and does not effectively embrace molecular symmetry as does MO theory. See also, linear combination of atomic orbitals, molecular orbital method, MO diagrams, ligand field theory, crystal field theory, references. External links, covalent bonds and molecular structure, hybridization flash movie, hybrid orbital 3D preview program in OpenGL, understanding concepts, molecular orbitals.